Just start the recording now. Yeah, we'll mostly use a sub-threshold operation for low power. So, we have a familiar term, mobility shocks, W of L. We have a body vector coefficient gamma divided by 2 square root, this is V silicon. And thermal voltage square, this is very small, right? Yeah, this is around 1. Vt square is very small. And exponential VGS minus VTH of MVT, something like that. All right. So, this homework comes too early. Okay. So let's talk about the parameters required for Handel analysis. We need 4 parameters for Handel analysis. This VTO is threshold voltage, VBS equals 0, gamma equal body effect coefficient. This Kp is mu Cox. Lambda is the channel length modulation factor. So we wanna derive those 4 quantities. Okay. So let's try to find one. So let's see. Yeah. So VTO thing is let me see. Yeah, we assume this is our measured data. Chapter 1 MOSFET is what? Yeah. Yeah, this is ID VDS, right? So can I write it here? Nope. Yeah, this is drain current versus gate source voltage. I think drain source voltage is what? Drain source voltage is 0.01 or something. Where is my? Yeah, 0.1 volt. Okay, my drain voltage is 0.1 volt, right? That's a drain source voltage. Then my back bias is 0, -1, -2, something like that. Okay. Then how can I calculate the threshold voltage? I just draw a straight line here, and then I find this one is just VTH plus 0.5 times VDS. Okay, VDS is 0.1 volt here. All right. So I can find the threshold voltage here, there. So this should be VTO. We can do this thing similarly. Okay, let me find the values here. So I select this one, and then I find so this value is say, so around this value is my threshold voltage VTH plus VDS divided by 2. Okay. Then say let's see. This is around what's the current level around here? Oh, this is around 7 microamp, right? If my current is 7 microamp, is it true? Yeah, maybe 6 microamp. Okay, then I can calculate my VDS in a different way. Okay, where is my VTH here? Oh yeah, here. So here, see, I edit it. Then you see this M1 is NG0 MB means drain and gate are connected together, so it's a diode, right? MOS diode. and then I apply current 10 microamp is too much. So I can apply like 6 microamp. Then see, I change my substrate voltage from 0 to -3. Okay. So it's something like that. So let's see. No, that one is just this one, right? So I sweep VBS from 0 to -3, right? Then we'll find this voltage, right? So I will draw. Maybe this way, -3, 0. And I can find something like that. So at the VBS is 0, this is my VTO, right? This slope maybe, I can, from this slope, I can calculate the gamma. Okay? Okay, so let's do it. So, you can see, yeah, this is the circuit, right? Okay. You can find it, NG 0 MB, right? This is my MB. Okay, I have zero NG means, see, from 0 node to NG, current flows from 0 to NG node, right? 6 microamp. So VB MB equals 0, I sweep this voltage from 0 to -3. Okay, I print out this gate voltage. Okay, so simulate and then find this one, calculate node NG voltage. Okay, so what's my VTO here? My VTO is how come I cannot prove? Oh, okay. How come I cannot trace this value? What's the problem? Something wrong? So my threshold voltage is around 0.7 volt, right? That's my VTO. Okay? Then I can calculate the gamma by plotting this one into different way. Yeah, this is a PHI which is around 0.8 volt, maybe 0.9 volt. It doesn't matter too much. So should be something like that, right? It should be straight, ideally straight line. This slope is my gamma because my VTH is VTO plus gamma square root 2 pi f minus VBS minus square root 2 pi f, right? Any questions? I assume the SPICE simulation result is my measured data. Okay. Then let's try to calculate KP and others. So let's see, where is my KP? I can derive my KP. Let's see. How can I calculate my KP? Oh yeah, let's yeah, I can calculate my Kp here. Oh, from diode equation I can draw my Kp, is it right? Yeah. So let's just see. Let's change this one a little bit. Yeah, let's change this one. So let's see, level 10 by 2, ng. Okay, this thing, I will change it into something else. We monitor dd, ng, dc0, and then, let's just see, vd, dd, 0, dot sweep, MB equals 0. Is this right? Yeah. This MB is shorted to ground. And then, oh, this is temperature very, how come this, my temperature very cold? At room temperature. I'll draw current. Okay. So I have a diode connection and then apply some voltage there and then try to calculate my, am I open? Yeah, open it. Where is my Kp? Oh yeah, here. Let's look at it. Yeah, looks fine. Okay, simulate graph. And then, it doesn't work. I got some problem here, right? VDD? Okay. Oh yeah, looks like, yeah, it's VDD. You're right. How come this is so rough? Oh yeah, this is 1 volt, right? 1 millivolt. So here, see, you can see this is a drain current. This is a gate source voltage. Actually, gate and drain are connected together. And you can see this is my threshold voltage. Now I can see threshold voltage around 0.7 at the zero bias. And then this is just a VGS minus VTH square. The multiplying term is Kp times W over L. Okay? So you can draw square root ID. Yeah, so the current equation, this is VGS equal VTH, right? So it's something like that. Yeah, this is my VTH. My ID equal in a saturation region. So I neglect my channel length modulation. This is my KP, right? So if you plus square root ID versus VGS minus VTH, so it will look like that, right? So, oops, sorry. Okay, something like that. So you can get KP. Okay, let's go to the lambda, channel length modulation factor, lambda. Okay, then let's move. Where can I find the lambda? Yeah, so let's see IDVD. IDVD2. Yeah, that's good. This one. Let's look at the netlist. Oh, yeah. Okay, gate voltage 0.2, 0.3, 0.7. Okay, let's simulate it. Yeah, this is kind of difficult. See, this slope is actually, yeah, from this slope, you know, this is this curve is just this current, actually this current times 1 plus lambda VDS. So, you know, this slope is lambda VDS. No, lambda. Okay, so that lambda is just this current divided by this current. Okay, that's my lambda. So here, what's the amount of this current? This current is say something like this is a 10 microamp. Yeah, this one the abscissa is maybe 9 microamp, and then this is around 5 microamp, and this is 9 microamp. My lambda is too large. Wow, how come? 5 divided by 9. Ooh, that's too much, right? That's too large. So my lambda is no good. But here, let's just say, let me eliminate this blue one. Okay, how about this green one? So this abscissa is around what? Around 1.3 microamp. And then what's this value? This value is around, oh, this is pretty large, right? This is pretty large. So, this is 5. My lambda is almost 1, is it right? Oh, sorry. I was wrong. I didn't use this is 3 volt. Okay. So, you know, this slope is actually lambda VDS. Lambda times this 3 volt, okay? Lambda times 3 volt. So my lambda is still pretty large. Okay. Wow. Then my voltage gain may not be very good. So let's change this one into channel length. So my lambda is too large. So I just change my channel length into something else. Yeah, L equal 0.7 micron. So I just assume this is L equal 2 micron. Okay. Okay. Then what happened? Yeah, this time it's much better, right? My lambda is reduced. Okay. So with the L equal 2 micron, I can calculate my lambda. I just draw axis like that, and then from this slope, this gradient, that should be my lambda VDS. VDS is 3 volt. Okay. So I can calculate my lambda by this slope. Question. Okay.